Okay, so we're about to end this day with a talk on evolution and programming. So, and first, Bas would like to start with
Don't spoil the
something
surprise, don't spoil the surprise.
extra.
First
So,
of all,
thank you.
yeah, thanks, sorry. Welcome all. In a minute I'll be talking about coding evolutionary algorithms. My name is Bas Kopper, by the way. But I would like to start with something else because it's a very special day. Next to the fact that this is the 10th anniversary or birthday of JFocus, as you'd like to say, it's also the birthday of my little boy, who has turned 1 today. Thank you, thank you. So you can imagine that I'm feeling a bit guilty standing here before you, giving a presentation in a minute. And I thought this morning maybe we could do something epic. Maybe we could give him a little bit of a birthday present. So I would like to ask you, and I know this might be a bit out of the comfort zone, to stand up. And I'm gonna tape a little happy birthday to you to send home. Thank you so much for engaging with this. It's really awesome. So I'm just gonna do a dry run. It's like happy birthday to you, happy birthday to you, happy birthday dear Olivier. Happy birthday to you, and maybe a bit of a hip hip hooray at the end. And then I'll send it home, yeah? So I'm gonna start the recording and start it by singing happy birthday to you, happy birthday to you, happy birthday dear Olivier, happy birthday to you, hip hip hooray! Gefeliciteerd! Thank you so much. The applause is for you guys. Thank you so much. It means a lot. It means a lot to me. And in the preparations, I haven't set this up yet. So we're gonna do it real quick. Because you haven't come here for singing happy birthday. That was a bit fun, right? You're here for evolutionary algorithms. Nature has always been a great inspiration to software engineers such as us. And I can name 2 great examples. I can name many, but I will name 2. The human brain, which invented the wheel, created the Roman Empire, created Java, and created JFocus. And there's another one, hint, it's in the title, evolution, which in turn created the human brain, as it is now. And also made sure that this little feller has a skin which makes sure he can blend in its environment so he could survive from predators. But before we get into how we can use the powerful mechanisms behind evolution to our gain, let me introduce myself. My name is Bas Knopper. I'm Dutch. I'm a Java developer working for a really cool company based in the Netherlands, J-Driven, an IT services company with 35-something senior consultant Java developers, several pizza/sushi sessions a month. So really fun, gained some weight, but it's all in good spirit. I have 10 years plus Java experience, and I've had the privilege to be talking at Java 1, JFall, GeekOn, and now JFocus as well, about one of my favorite topics, as I'm an AI enthusiast with a soft spot for evolutionary algorithms. So what would I like to accomplish today? Is for you to be or get interested in evolutionary algorithms and its design and how it works. I would like you to gain some basic understanding of the concepts behind evolutionary algorithms. I would like to show you how to use them and when to use them. More importantly, when not to use them. And I would like to add evolutionary algorithms to your already magnificent toolbox that you as developers probably have. And last but not least, I profoundly believe that AI techniques and evolutionary algorithms, as one of them, don't get the attention they deserve. Though the last few years, it has seen an increase in in that. So if you're on Twitter, use any of these hashtags or my Twitter handle to show the community that evolutionary algorithms can be really cool and they actually fix problems. So what's the agenda here? Well, saying happy birthday, thanks again. A little introduction I just did, and we're going to start off next with a little example from NASA, who actually use evolutionary algorithms for a really practical use case. I'm going to show you after that what the evolutionary concepts are that make it possible. It's going to be only for like 2-3 slides. Then it's puzzle solving time. I have the traveling salesman problem as a use case to fix to fix the traveling salesman problem, solve it with an evolutionary algorithm. And it's actually used to show you the design of an evolutionary algorithm using plain Java code. And I'm going to show a demo that it actually works. So that should be fun. I did some plain Java code so I could present it as such. But there are also some frameworks that can give you a running start if you're interested, and I do hope you'll get interested. And last but not least, we'll have a checklist when and when not to use evolutionary algorithms. Sounds like fun, right? Great. The happy birthday thing was a good warm-up. So NASA, everything NASA does is cool. So when I show you they did something with evolutionary algorithm, it must be cool, right? So they did a Space Technology 5 mission, as it was called. And what was so special? They used 3 full-service 25-kilogram class spacecraft. Bit of a mouthful, but what it means in this instance is that they were really small. They were like a small TV set, 3 of them orbiting Earth, doing some interesting NASA stuff. And you can see in the pictures how small they will be. By the way, the left one is not the new splash screen of Eclipse, but a rendition of how it would look like in space by some artists. So we have these small spacecraft. So they need an even smaller antenna that would still need to function according to the spec. You still want to be able to communicate with those things, right? So that's a need for a solution that's not easy to engineer. And engineers actually couldn't solve the problem. I now see that I have a screen over there, which is way better, so I can walk around a bit. So they used an evolutionary algorithm that made these. And notice how small they are. If you would give me pen and paper and ask me, hey boss, would you please draw a really small antenna for me that you think would still work in outer space that small? I wouldn't draw these. And so did the engineers at NASA. So they used an evolutionary algorithm that made these for them. And it's easier if I just showed you. Small video by NASA itself, promo video of evolutionary algorithms, and how they actually came to these antennas.
Evolutionary antenna synthesis. Designing and optimizing antennas by hand are time and labor intensive, are costly, complexity is limited, and requires significant expertise and experience. The Evolvable Systems Group at NASA Ames Research Center tackled a challenging antenna design problem for NASA's Space Technology 5 mission. They've come up with a computer program that searches for superior designs by repeatedly taking the best antenna designs and using them as parents to breed new ones. "35 network computers running advanced evolutionary algorithms, generating hundreds of thousands of antenna designs. The survivors go on to produce ever higher performing populations, leaving but a few superior designs. Evolutionary antenna synthesis has the potential to design better and less costly antennas faster than before. The evolved antenna is currently undergoing tests that will tell if it is qualified to launch with 3 satellites on the Space Technology 5 mission in 2004. If successful, this evolved antenna will be the first evolved object to fly in space.
That's pretty cool. And this session is about showing you how they did that. A small recap, I think this is a powerful example of how evolutionary algorithms can be used, since it was a problem a human being couldn't solve. So they used evolutionary algorithms to solve it. Powerful example. It is actually the first evolved object to travel through space, because at the end she said undergoing tests might be the first evolved object, etc., but it actually happened. They created a working antenna with an evolutionary algorithm, and it traveled through space. How awesome is that? So how did they do this? Well, to get into that, I want to show you a bit how evolution works. You probably already know a bit of a recap, because evolution is at the basis of all of this. So, the first thing that pops to mind most of the time is survival of the fittest. So what is survival of the fittest again? Well, in an environment where you have finite resources, I'm talking water, food, maybe a place to sleep, and life forms with a basic instinct toward reproduction. So these individuals start growing, more individuals. The resources stay pretty finite. Then you have natural selection, because some of them are competing better for the resources than others, and they tend to survive. Natural selection, probably already know about it. Want to point it out anyway. Because there are some interesting mechanics behind it. So if you look at these expertly drawn individuals that mark some characteristics through color and form, shape, you can imagine this as being a population. Some tend to not survive because they can't compete for the resources as well as others. It's a little bit like the too bad. Others can, and they reach an age where they actually can reproduce with another individual. It's also called recombination. They recombine their respective DNAs, or half of it at least. You get a new offspring, new child, with traits from the one and traits from the other. Sometimes during this process of recombination, something magical happens. Anyone have an idea? Mutation, very good. Mutation happens. So what does this mean, mutation? Well, sometimes, I guess you already know what mutation means small change during the recombination. You get a different gene than you would have if it didn't happen. So what does this mean? Well, sometimes you get a really cool new skill or trait that pops up in the population that wasn't there before, making the individual competing way better than other individuals. So, and afterwards he can reproduce. And the trait goes on and on and on in the population and is a new trait in the population as a whole. There's also something else that can happen. It can be really, really bad to have this new skill or trait or gene, because it makes you inviable. Maybe doesn't even makes you survive birth, for example. And another thing can happen, which most people tend to forget. Nothing happens, because you don't notice it in the individual. So we have our parents that survived, made offspring. Fortunately, we have some that didn't survive. So our new generation looks like this. And we're competing for the same resources again. So you can imagine this going on and on and on and on and on. And eventually, the individuals are fitted way better to the environment than the first population. So this is all nice, evolution theory, okay, fun. But we're problem solvers. How can I use this to solve my problems? Well, how do you get from evolution to problem solving? If you view the last picture, and you see the environment as the problem to be solved, then you can look at an individual as being a candidate solution. And the thing is, generation upon generation can take a while to simulate, but not for a computer. It depends on the problem and on the solutions. But 100,000 generations is nothing for a computer. Could happen in a couple of seconds or a few minutes. Now these mechanics become very powerful. It has taken us a lot of years to become who we are, but a computer can simulate that in way less, which makes it interesting to use evolutionary algorithms. So that was a bit of the theory behind evolutionary algorithms. Let's head on to some puzzle solving time. And I'm going to use a literally more down-to-earth example than NASA. It's called the Traveling Salesman problem. You might already know it, but I'm just going to explain a little bit about it in one slide, just so we're up to par. So given n amount of cities, n is the number of cities to visit, you as a traveling salesman need to find the optimal route for visiting all cities. You can imagine being a traveling salesman from Stockholm. You want to visit all European cities and be home before dinner. That's pretty impossible, but you get where I'm hinting at. There are a few constraints though. You can visit every city only once, and you have to return to the origin city. So that's basically the problem. Well, this sounds fairly easy, right? I explained it in like 3 bullet points. But the thing is, the search space is huge. For 30 cities, there are 30 factorial, that's 10 to the power 32 possible routes. That's this amount. I mean, I don't even know how to pronounce this number, right? Brute force might not be the best solution. So, also, by the way, evolutionary algorithms is not the best solution, but I'm going to try to show you that it will solve a problem which for brute force would be very, very tough. So this is a use case to show you evolutionary algorithm design, because we do have to do some design up front. I'm going to show you some plain Java code that implements this design, and I'm going to show you a demo to actually show that it works. So, what does this evolutionary algorithm look like? Well, we'll start with the initialization of the population with random candidate solutions. You can imagine that as a first step, right? We just want some random candidates. But what is a candidate solution? Good question. It's a representation of a solution for our problem. So in our case, for the traveling salesman problem, say we have an n equals 6 traveling salesman problem. We could just label the cities 1 through 6. Take base city 1, then a candidate solution signifying the route could look like this, which is just 1, 2, 4, 3, 6, 5, 1 is a possible solution. Could also have been 1, 3, 5, 6, 4, 2, 1. But this is a way to represent it, for the algorithm to work with it. For n equals 10, it would look like something like this. And this enables us to calculate the distance, which is going to be our fitness function. I'll come back to that later. It enables us to do mutation, and it enables us to do recombination. And it's really important to think about the representation, because it will affect the way you have to do recombination, mutation, etc. in your code or in your design. So now that we have our candidate solutions, our random candidate solutions, we are going to evaluate each candidate, because we want to know how good they are for our problem. So this is also called an evaluation function or a fitness function, which is a term you probably already heard. And in our case, it's fairly easy. It's just the summed distance. So you take the distance between 1 and 2 in this case, 2 and 4, 4 and 3, 6 and 5, etc. Sum it up. That's your fitness. So fitness could be 6,000 miles. and I use NASA and Whirlwind in the code I'm about to show to calculate these distances. Just use the library for it. And what we want to do with this distance is to minimize it. So normally the fitness you want to maximize, but to keep it conceptually more clear, we're going to minimize the sum distance because we want a low distance. There are some tricks to like 1 divide by distance, and you have the same, then you can maximize it, but I want to keep it conceptually clear. So we're going to go for minimizing the sum distance. Some Java code. Yay. So what we're going to do here is we're going to implement this calculate fitness, which should be easy. So this calculates the total distance of the whole route and stores it as its candidate solution fitness. So what we see here is we have a candidate solution implemented. It's a class. This is a method in that class. And what we're going to do is we're going to initialize the total distance of 0. We're going to calculate the total distance. And we're going to store it as a field. This is a pattern we've seen 1,000 times already, right? For many things. So what does this calculate distance look like? Well, for all cities in the route, except for the last one, we get the distance between this city and the next, and we add it to the total distance. Why not the last one? Because it doesn't have a next. And what we do is we get the city on index I, get the next city, I plus 1. We calculate the distance. This is done by the NASA Whirlwind library. And add it to the total distance. This is it. This is our evaluation function. Now we have a fitness for each candidate solution, and we can work with this. So we have population. We have evaluated each candidate. Now it's time to get into the loop. Right? Now it's time to create generations and generations and generations. But we're programmers, we're developers, we hate the word infinity. We don't do while true. We want a termination condition. The funny thing is, evolutionary algorithms are stochastic. There are parts of it that are based on probability. So you can never know when it will terminate or when it finds an optimal solution. So then it's a good thing to look at the behavior of an evolutionary algorithm. And it looks a bit like this, which is a logarithmic growth function. And the funny thing is, this is why we use a combination, or you could use a combination of something sure to terminate. Time, I'm going to run it for 3 minutes, I'm going to run it for a year. Maximum number of runs, as in generations, I'm going to run 10,000 generations. So the combination of something sure to terminate and the goal. I want the fitness threshold to be 6,000 miles, so I know I can make it home before dinner. That will be a good solution for me. So as soon as it hits under 6,000, you're done. I want that route. Another interesting thing is, and I really like this one, is fitness improvement stagnation, which basically means if you look at how an evolutionary algorithm behaves, then you could say, okay, the progress in the first half is way more than the progress in the second half. So if I see a stagnation in the improvement, you could just call it quits. Maybe you need to do some optimization if you still haven't hit the fitness threshold you'd like, but this is a good way to test, to fit you with the dials a bit. So we're in our while loop. We have a termination condition, so we know it's going to end. So what are we going to do now? We have a population. We want to create some generations. So first thing we do is we select the parents we want to recombine, mutate, etc. So parent selection, there are a couple of options. And they're not all on here. So where X is the number of parents, you could just pick X best. I want the 10 best parents, 10 best candidate solution, and pick them as parents. It's a good way to go about it. You could also pick random X. Anyone an idea why I would pick random? Yeah, sure. You don't have to put it here, just throw it out there.
Get out of a local minima.
Oh, that's really specific. Okay. I wasn't going to go about that deeply, but you're...
Local maxima, I mean, of course.
Yeah, I know. Well, both. Yeah, exactly, because you want to keep genetic diversity. So maybe you're building up to a solution while there's a bigger solution over here. So you want to keep genetic diversity so it can also climb the other mountain. You can also do a combination of these by saying, okay, I want to pick best X out of random Y. So you keep the genetic diversity, you keep the thought that you have picked some of the best. So in our example, we will use the best X out of random Y. And let's look at some code again. We're going to implement this method. It's called parent selection, and it returns a list of candidate solutions, which are our parents. And we'll just initialize with a temp population. Be clear in a bit why I'm doing this. And we'll have some random candidates. So first we want to create the parent pool, which is the random part. And again, this is a pattern we've probably seen already. We select a random candidate solution from the temp population. We get it, so random index, use the index to get it. Then we add it to the random candidates. And this is the reason why we need the temp population, because of that concurrent modification exception. Which is the reason I need the temp population. Because we don't want to pick the same parent twice. So now we have a random candidates. And this is really cool. We're going to sort the random candidates. Why would I sort the random candidates? Anyone an idea? Just shout it out.
Evolution pressure.
Okay, I know what you're saying, but this is more of a technical thing. As in, how is sorting it helping me to get the best?
Sort them on fitness.
Yes, exactly. So I just implemented a comparable, which said, hey, if this one is smaller distance than this one is bigger. So now I have my fittest candidate solutions at the front, and my not so fit candidate solutions at the back. And now I can just return a sublist of this random candidates list to the parent selection size. By the way, you see this parent pool size. Let's see, where is it? Here. And you see this parent selection size. Those are variables. Because we want to fidget a bit. Fidget with the dials with our evolutionary algorithm. I'm going to show you in the demo that they are actually parameters you can change, which is why they're in blue, and which is why I haven't, which is shown as such now. Just to make that clear. So we have our parents. Now we want them to recombine. So how do we go about that? Well, in our example, half-half doesn't work. So I have half the DNA, normally with us, it's like half the DNA of the mother, half the DNA of the father, smash it together, 9 months later, ta-da! Why wouldn't that work in this situation?
Might not go through all cities.
Exactly. You might not go through all cities, and you might visit a city twice. Very good. So what we do is cut and cross-fill, which is one of the difficult things to explain now, but it's still fairly easy. So we pick 2 parents, and we want to create 2 children. But I'm only going to show you one, so it's easier to follow, right? So we have 2 parents, and what we're going to do is first the cut part of the cut and cross-fill, and that is to pick a random index, which in this case was over here, and cut this part into the child. Okay, cool. What we're going to do now is the cross-fill part. So we're going to look at this parent, and we're going to cross-fill from the same index point. And what is this cross-filling? Well, to prevent visiting the same city twice, we're going to look at the cross-parent and from the cut index on and check, hey, do I have this city already in my child? No, add it. Otherwise, move on to the next. So the 5 we don't have yet, put it in the child. 4 we already have, the 2 we already have, I'm just going to move this, the 2 we already have, start back from the beginning. Hey, there's a 3 there we didn't yet have, and a 6. That's how cut and cross-fill works. And now we have actually met our constraints. And you do the same the other way around, where you have the cut index here, and you copy it from here and do the cross-fill over there. 2 parents, 2 children. This is how we create our children. This is how we recombine. So what does it look like in code? Well, we have our 2 parent routes. We initialize an empty child route, or 2 actually. We randomize the cut index, we just randomly get one of the indices. We copy the first part of the parents into the children. It's just sublisting into the children. We perform crossfill, which is a bit larger, so I'm going to show it to you in the next slide. And after we've done that, we just use the new routes to make new candidate solutions. And those are our children. And we'll put them in a list and return it. It's omitted for layout reasons. Okay, so this crossfill, what does that look like? Well, what we're actually doing is just a for loop from the cut index point on to the end. We'll get the city, check if the child route already has it. If not, add it. Really simple. Back from the beginning. So here the for loop starts with 0 instead of the cut index. To the cut index on, same story. So, interesting question. Why not just start here and go all the way there? I mean, that's what we're doing, right? I mean, eventually, if you just put them together, you're going from left to right. Anyone have a clue, an idea? And this is what cut and crossfill makes it interesting. This is, you could do it the other way around, but there's a reason why it's done in this way in the textbooks. It's because we want to copy skills or traits from the parents. And what is a trait in this case? It's the ordering of the cities. So in this way, using it like this, you actually keep the ordering of the cities of both parents in some sort of way. Which is why we're doing it like this. So this is really simple implementation. I mean, it fits on one slide, but it's such a powerful concept that we've just implemented. And it works. I'm going to show you that in a minute. So, we recombine our pairs of parents, and sometimes we're going to do some mutation, which we're going to do with a certain mutation probability. And a change of number won't work. So, like, conceptually speaking, like intuitively, I see a question over there, I think.
When they combine,
Yeah.
is it okay that they make a child that has a worse solution than either of the parents?
I don't think I can relate this to humans without hurting people. But in evolution, there's also a chance that you have offspring that are worse than either parent or both. So yeah, I can imagine what you're hinting at, but that's also the beauty of evolutionary algorithms. They're going to make children that are awful. You know, they're not going to work. But you don't care. You care for the actual good solutions. But yeah, excellent question. So it will produce some offspring that is terrible, but in the end, it will actually work. Yeah. So for mutation, a change of number won't work because you can get an infeasible candidate solution, as we've heard before. Swap to the rescue. We have this candidate solution. We just randomly pick 2 cities on the route, and we swap them. We could implement it in another way, but this is fun. We swap them. As an evolutionary algorithm designer, I don't even know if you call it that. You get to design. Okay, mutation would be most optimal using this. I just chose to do this, partly because it was in the textbooks, but it's also intuitive. So what does this look like in Java? Well, you get a random index for 2 cities. You use that index. Oh wait, this is the funny part. Took me a while to get this bug. I noticed that some mutations weren't happening, though it did say in the log it was mutating. Make sure the indices are not the same. because swapping with the same indices it doesn't make any sense. Retrieve the cities on the given indices, just get the objects. Changer, we change them by setting it to the new indexes. That's it. Again, method on one slide. And the parts are not that interesting as you look at this code. But the combination of all the mechanics is really powerful. So we have selected parents, they recombined, they mutated, some of them, the children. And now we evaluate all the new candidates. We already seen how we do that. And now we have to select the individuals for the next generation. And then we go about it again. It's also called survivor selection. Who survives? Who goes on to the next round? It's also called replacement strategy. You could do nothing. I mean, it's a computer. We're simulating stuff. Nobody has to die. It's a perfect world. No, but kidding aside, you can choose to do nothing. You could replace the worst. And there are a couple of others. But we're just going to go with replace the worst because it's fun and it works for this situation. So select survivors. We're going to sort the population again because we have this magnificent comparable. And we just sublist the population size back. That's our survivor selection. It's like effectively 2 lines. Cool. So that was actually our evolutionary algorithm. There's some tuning to be done. There are a lot of variables I just named that you have to tune, like a mad professor, fidget with the dials, see if it works. It's also one of the fun parts about evolutionary algorithms because you see things working better when you change the variables. So mutation probability is one of them. Do I mutate every time? Do I never mutate? Population size, is 100 a good population size? Is 1,000 a good one? Number of offspring, termination condition, parent selection, which kind of parent selection do I implement? Survival selection, initialization. Do I do a random initialization or do I want the first candidates to already have a good solution or a semi-good solution? Funny thing about evolutionary algorithms is, we already talked about the behavior. In the beginning, it skyrockets fitness-wise. So a lot of people are saying, why would I bother doing heuristics to get a bumped up initial population if the evolutionary algorithm is going to do it for me anyway? So those are some interesting thoughts. Actually, what's funny is, I think there's a whole section of academics concentrating on evolutionary algorithm, tuning their variables for their evolutionary algorithm. That actually works, and it makes sense. It's mind-boggling, but really cool. So it's demo time. The backend is really the Java code I've just shown. True story. And I implemented the pseudocode, which isn't that hard. And I used the NASA whirlwind to do calculation on the backend. The front end was a week before Geek on Prague, hacking night. I just thought, you know what, let's do a front end, Angular, Bootstrap, Google Maps. Turned out pretty cool, to be honest. Hope it works. You can fork me on GitHub. I uploaded the latest version a few days ago with a good README now. So you can just set it up in like 3 seconds because you run a Gradle and you run a simple Python HTTP server. And you're good to go. So, sorry? Oh, the slide in GitHub. No, but I will post it on Twitter. And that's actually a good suggestion. I'll put it on GitHub as well. Thanks. I'm here, but that isn't. Oh, this is because of... Some of you are probably wondering, why is he using PowerPoint on a Mac? I know. This is what I was looking for. There we are. Ooh, this spoiled the surprise a bit. Let's do a refresh. The Wi-Fi is great here, by the way. It's really good. J-Focus, you know your... Okay. Okay, let's start over here. I'm going to explain a little bit. No, I have 10 minutes left, so I'm going to... There we go. So these are these variables we talked about, right? And it's fun for you to maybe download the demo and just fidget with it a bit to see how it feels. We don't have the time for it now, so I actually defined some presets to make this demo a bit smoother. Let's see. Yeah, let's put it like this. Okay, and yeah, there we go. And over here, we have a nice graph showing the current fitness. And hopefully we'll see a nice evolutionary algorithm graph, right? I took the capitals of Europe. Let's do some traveling salesman problem solving with evolutionary algorithms on the capitals of Europe. Here's the generation, the fitness. Side note, warning, we're going to start with low. So, just so you know. So this is a low setting. And you saw some changes in the beginning, but this has a really abstract form of the evolutionary algorithm graph I just showed earlier, which is already a sign that it isn't working that well. So what I'm going to do is I'm going to set it to medium, and you see that population size got a bit higher, number of generations, so it can actually do its thing. Parent selection size changed a bit, fitness threshold. We're going to run it again. And we saw some movement there, but it's not really, this doesn't really look like a good solution. Right? Even we can see that it's not a good solution. And again, you have this really steep incline and then nothing. I feel the tension a bit. No? Is this going to work? EAs are stochastic, right? Okay, just checking. Let's do it again. Oh, now we see some things. Now we see some things happening. It's probably the mutation probability of 90. But hey, it's doing something. And look at this beautiful, semi-beautiful graph. I've seen some better graphs. But it's looking like something now. The solution is a little bit prettier than the ones before. And the fit is actually a lot lower, below 13,000. But I know it can do better. So I'm going to run it a few more times. It's just, I think that this is art. Like, it's moving, and you see the evolutionary algorithm do its thing. There we go. It's always so stressful when showing evolutionary algorithms and having to show that it works. Okay, so this is already better than the one before, but we have a mutation, so let's wait for it till 20,000. Then I'm going to do it one more time. For some reason, it's always the third time. There we go. So you can play with this by downloading the code, cloning the GitHub repository. This is not my day. Although my son's birthday, so it should be his day. Yeah, there we go. Come on! Oh man! Okay, one quick more time, and then. But the funny thing is, so this is a high setting, but it's, as I said, stochastic. It's just fun to play with the variables and see it working. This is actually, oh, okay, there we go. This is one of the better ones. Yes! I told you it's a third time, every single time. I should check the code. I think someone is like messing with me.
How about the fourth?
How about the fourth? Maybe even better, yeah. No, I don't want to change this. I want you to leave seeing this beautiful picture of a traveling salesman that can do a normal route after a few tries. But this actually works. How cool is that, right? Great. Oh. So I have a few more slides for you, yeah?
You had a very
Yeah. Well, it implies a bit that the recombination strategy could be a bit better. But there are domains where a high mutation probability is a good thing, and there are domains where a low mutation probability is a good thing. The thing is, even within the traveling salesman problem search space, suppose I picked all the cities in Africa, or all capitals in Africa, that might be a whole different search space with different local maxima. Maybe this search space has a lot of local maxima that you have to jump out of using the mutation. So yeah. I only have a few minutes left, so I wanted to show you one or two more things. So, as I said before, plain Java code, but if you want a running start, there are some very good frameworks out there. Watchmaker framework is a bit hipper, newer framework, although it's a couple of years old, and I don't know if development's still going on, but it has a lot of good demos and a way for you to work with evolutionary algorithms. JGAP is a bit more of the scientific kind, if you know what I mean. So not as hip and everything, but it's a really good framework to work with. There are a lot of others. I'll put the slides online so you can check this for reference later. But with great power comes great responsibility. So here's a little checklist to see if you should use an evolutionary algorithm in the future somewhere. And the first question I always ask is, are you sure you can find a brute force approach that works within a reasonable amount of time? Because then just go for that. I mean, don't bother using an evolutionary algorithm unless you think it's fun. Am I facing an optimization or a search problem? Evolutionary algorithms tend to be really good at those. Can I encode a candidate solution to the problem? Is representation possible? If you can't represent it, then you can do mutation, recombination, etc. Can I determine the fitness of a candidate solution? If you don't know which is better, how are you going to check which one survives, which one should recombine, etc.? And if all answer yes, just do it. It's fun to work with. It'll blow your mind. It's amazing. So one does not simply end the presentation without answering questions, but seeing as we're running out of time, I think this is the last presentation, so come up to me after the presentation and I'll gladly talk about it. I'm very enthusiastic about the subject. If you have additional questions, which you didn't ask, but anyway, contact me on my Twitter handle. Google it. There's lots to find. Papers, demos, the aforementioned frameworks. Really cool. Thank you guys. Have a great day.